the problem reads as follows. Evaluate the double integral x plus twice y dA over the region D, where D is the region bounded by the parabolas y equals to 2x squared and y equals to 1 plus x squared. Now whenever we encounter a domain or D or region of the integration where the region is not really rectangular, then the first thing we should do is have an idea. To have an idea of the domain, we should sketch the how the domain looks like. So here the domain is the region bounded by these two curves. So let's first draw a sketch of y equals to 2x squared. Okay. It's since y equals to 2x squared is a parabola, it should look something like this, touching the origin. So this is y equals to 2x squared. Next we will draw the second region, y equals to 1 plus x squared, which looks exactly like y equals to x squared, except every coordinate of the parabola is shifted 1 unit upwards. So since the vertex was at the origin, it will now move 1 unit up at y equals to 1. And y equals to 1 plus x squared is also less steeper than y equals to 2x squared. You can test it out if you take the derivatives, although it's not necessary. So if I take the derivative of this will give me 4x, and if I take the derivative of this will give me twice x, which means this is twice as steep. So when drawing 1 plus x squared on the same diagram as y equals to 2x squared, we should draw it more flattened than y equals to 2x squared. So let's draw out the more flattened curve, and we know that it must intersect the y-axis at y equals to 1. So this is y equals to 1 plus x squared, and well, we can see that this region is the bounded region. This is in between the two curves, right? So our D is actually this shaded part, and the bound of the D. In order to declare the bounds of the D, we need to know these intersection points. Where do the curves intersect? Now, since it's quite difficult to draw on this board, I have the diagram prepared. So this is the cleaner diagram of the same thing. So this is our domain, as you can see, starting from here at one intersection point and at another intersection point. Here the intersection points are given. However, when solving the problem, we need to find the intersection of these 2 points, so of these 2 curves. So let's try and do that. So one of the curves is 2x squared and the other one is 1 plus x squared. So in order to find the intersection points, what we have to do is to set the x coordinates as equal. This will give us the x coordinates where the curves intersect. So this is just x squared equals to 1, which means that x is equal to plus minus 1. So the x coordinates of our intersection points are at plus 1 and minus 1, as you can see. We don't really need to find the y coordinates to solve evaluate this integral that we are given with, and this is the integral of x plus twice y over this domain D. So the first thing we need to do is to set up an iterated integral, which will for which we will need to find the limits, and since it's non-rectangular, we need to find either using a type 2 domain or a type 1 domain. Now for this particular problem, using type 1 domain is easier, and let's try to do that. So as you can see, any point in this bounded region is actually above this curve y equals to 2x squared, right? Any point in this bounded region has to be above the y equals to 2x squared function. So we know that the y coordinate of all of these points must satisfy that it's above 2x squared or on this line 2x squared, and then it must be either below or on y equals to 1 plus x squared. Similarly, now we'll find the x limits. Now all of these points have x coordinates which must lie between -1. it may be this particular point where it's -1, or if it's towards the right of this point, this means the x coordinate is greater than -1. Then it must not exceed +1 over here, otherwise the point will lie outside this region. So it has to be less than or equal to +1. Now this is a logical way of finding type 1 domain. However, there is a much easier way. So to find a type 1 domain, what we do is start a small vertical line at the bottom of the y-axis in our sketch. It should be below all the curves that we have drawn. So this can be a starting point. So we will move it vertically upwards, and the first curve this arrow will hit. Let's say we imagine that we're moving this arrow in the vertical manner. The first curve that it hits has to be the lower limit. So while setting up the integral, it should be something like, so the first curve is actually this curve, right? So this is 2x squared, and then we'll keep on moving the arrow, and the second curve that it will hit will be the upper limit, and we know that this curve is y equals to 1 plus x squared. Great. Now finding the x limits or the limits for the outer integral for a type 1 domain is much simpler. It is simply the coordinate which has the smallest x value in the region. So you can see the smallest x value in this region will be the one which is the most towards the left. For instance, this particular point will have the smallest x value, as if we are moving right horizontally or parallel to the x-axis, the x values will start to increase, which means this must be the x value which has the smallest, the coordinate which has the smallest x value. So our lower limit is going to be -1, and the one which has the highest value for the x coordinate in our region, which is this one, and this is the rightmost point. We're kind of informally saying that any point which is most towards the right is definitely the point which has the highest value for its x coordinate. So here it's this one, right? So it should be +1 as the upper limit. Now that we know the limits for our iterated integral in the order where we do y first and x later in a type 1 sort of situation, so let's do that. Now here is what our function we should have our function here. So here let's write down x plus twice y. We do the y integral first and then the x integral. So x will be treated as a constant when we do the inner one. So let's this means that we'll have y. It should be y squared by 2, right? So and there is 2 over here, so the 2 will cancel, times dx. Now we have to keep the limits. We have to remember to put the limits in. So now we will put 1 plus x squared in the places of y. This has to be subtracted with this is the lower limit. Now we're placing a 2x squared in y's place. So we have the 2x squared. So let's simplify this a little bit. So this will be x plus x cubed plus we have 1 plus 2x squared. This is just the square formula. So plus x to the power 4, then we have minus 2x cubed, and here minus times this, so we've got minus 4x to the power 4 times dx. So let's now simplify a little bit. So let's start with the highest power. We should have, if we combine these two, minus 3x to the power 4, then let's try x cubed. So this 2 will give us minus x cubed. Now let's try x squared, plus 2x squared plus x plus 1 times dx. So now it's just a simple integration of one variable. So we have minus 3 by 5 x to the power 5 minus 1/4 of x cubed plus 2/3 of x cubed plus x squared by 2 plus x. I should take the limits from 1 to minus 1. So now we just put in the limits. First, when we put x equals to 1 here, it should give us 79 by 60. And when we put x equals to minus 1 in this expression, we will get minus 49 by 60. This minus is because we're doing the lower limit, and this is what we get once you substitute minus 1 in this expression. Now once we evaluate this, we should get this is our answer. The problem reads as follows. Find the volume under z equals x squared plus y squared and above the region D in the xy plane bounded by the line y equals to twice x and the parabola y equals x squared using both type 1 and type 2 regions. Now, as before, the first thing we should do is draw a sketch because our region is not rectangular, the region D. So this is our sketch, and first we will solve the problem using type 1. So we will write our curves as if in terms of x, right? Like y equals to something in terms of x and y equals to something in terms of x, the two curves that we have. And to find the limits is quite simple. We should start from the bottom of our sketch and move up. The first curve we hit is our lower limit for y, as we're doing it in type 1. So we have the first curve that it hits, which is actually this one, y equals to x squared, will be our lower limit, and the second curve that it hits as we progress the arrow, which is the line y equals to twice x, is our upper limit. And the leftmost point in our region, as in the coordinate which has the smallest x value, in order to find these two values, we need to find the points of intersection, which is here. You can see it's in the origin, but let's do it anyway. So to find the intersection points, all we have to do is to equate these two curves or line. Let's do this. So y to find the points of intersection of x coordinates, twice x equal to x squared, and just setting this to equal. So x squared minus twice x equal to 0, which means that either x equals to 0, there is an intersection point at x equal to 0, and another intersection point, not right, another, yeah, just is really another x intersection point must be at 2, right? Because when x, if you put 2 over here, you get 0, so x equals to another intersection point is at x equals to 2, and this means that this point must be at have an x coordinate value of 2. So let's you can write it out, x equals to 2, and here we have got x equals to 0. So the leftmost point in this particular region is here, right? And this is at x equals to 0, and the rightmost point in this region as in left and right, as in parallel to the x-axis. So the rightmost point is here, which should be x equals to 2. So this is how we set up our integral. Of course, we do the x integral later. So let's do it. If you remember, the question asked for the volume, right? So the volume is just the double integral over this particular region. This question is simply telling you to calculate the double integral of z over d. So let's do that. So z is x squared plus y squared. So we double integrate z dA over d. And we have already established that if we do it in a type 1 domain, we will have this particular set of limits, x squared twice x. So we get x squared twice x. Then we have 0 to 2. And our z is x squared plus y squared. Right here. X squared plus y squared. Times, we do the y integral first, as it's a type 1 region, and then we do the x integral. Great. Now we'll treat x as a constant, so we get x squared y plus y cubed divided by 3. Now we plug in the limits. Just put twice x in the place of y. So now we put the lower limit. Now this term is just x to the power 2 to the power 3 equals to x to the power 2 into 3, and this is just x to the power 6. So let's evaluate this. First, let's just simplify. So this is just 2x cubed. This is 2 cubed is 8, so we'll get 8 by 3 x cubed minus x to the power 4, again minus 1/3 x to the power 6, because the x squared cubed is x to the power 6, so dx. Now let's do the simple integration. So we get 2/4, which is just half, 2 over 4, so 2 over 4 is just half, so x to the power 4. So we should get 8 by 4 into 3, or x to the power 4, but 8 by 4 is just 2, so we get 2/3 of x to the power 4 minus 1/5 of x to the power 5 minus 1 by 7 into 3 is 21 by 21 times x to the power 7. So we have 0 and 2 as the limits. So if I substitute 2 over 2 in this expression, you'll find that we'll get 216 over 35. And if I put 0, we'll just get 0, because 0 to the power any positive number is just 0. Now let's solve this problem by using a type 2 domain. Now again, from the question, if you remember, it's actually written in the question that our domain D is bounded by the line y equals to twice x and the parabola y equals to x squared. So we'll just simply restate that y equals to twice x and y equals to x squared. So if I want to do this in a type 2 way, which I should now y is written in terms of x, like y equals to twice x or y equals to x squared. I want to write x in terms of y. So it's basically interchanging the subject and object. So we get half y, x equals to half y, and here we'll get x equals to either positive or negative square root y. So, but of course we can only have one of them. We have to determine the correct one using a sketch. So the sketch of the domain won't really change. So before writing this one, let's just look at the sketch. The sketch won't really change. The domain does not change. Either I write my curves in using x or y, the sketch or the domain will actually be the same. So in this domain we can see that all the x points are positive, because this is towards the right of the y-axis, or y-axis is also where x equal to 0, right? So every point in this domain is either, or over here is x equals to 0, or either it's definitely going to be greater than x equals to 0 for all the other points other than this one. That means that x is positive or non-negative. So it's either positive or 0. So here of course we have to pick the positive square root. Okay, so let's rewrite this. So x equal to square root y, and then we will identify which lines are this. So this is a straight line, y equals to twice x. It's the same line, just x and y, their way of writing has been changed. So x equals to half y is this line. Let's use a different color. So this is x equals to half y, and this is our curve x equals to square root of y. So how will we now find our limits? From the definition of a type 2 domain, our x limits are going to be described by functions, and the y limits will be constants. So let's start with x. Here we'll use a very similar idea as we did before. Instead of starting a small arrow in the direction of y-axis, we'll start a very small arrow from the very left part of our graph, which is still which is going to cross our domain. So this is going to move towards the right instead of vertically upward. It will move along the x-axis. Will move towards the right. Imagine this arrow is moving. The first curve or the line this arrow will hit will be our lower limit. So we'll get this as our lower limit. This is the line. So x equals to half y is our lower limit. And as we move along the arrow, the second line it hits is this curve. And this curve is x equal to square root y. And similarly as before, the smallest y value in this particular region will be our y limit. So you can see from this region the y limit must be at 0, because all of these coordinates have a y coordinate value of either equal to 0 in here, or it's above this point, right, vertically upwards. So this is our smallest y value, which is at 0. So as we move along, the topmost point is here, which is at y equals to 4, and this is our limit written in a type 2 format. So let's evaluate this. So our volume equals to the double integral over the domain D, and the function is still the same, x squared plus y squared times dA. And let's write this in an iterated integral using type 2 domain. So it's half y, square root y, 0, 4, we do the x integral first, treating y as a constant. So we have x cubed over 3. Here is just y squared x, as x is being treated as a constant. And we write the y limits times dy. X integral is over. So now we just substitute the limits. Get 1/3 y to the power half, the square root is just y to the power half, to the power 3 plus y squared times y to the power half let's write it this way, minus one-third times half, we just substitute the lower limit here, half y whole cubed plus y squared half y, and this has to be done again in dy. So now we just simplify this a bit. So this is a y to the power 3/2. This will be 2 plus half, which is 2.5 or 5/2. So plus y to the power 5/2, and minus, this is 1/8, as half cube is 1/8, times 1/3 is minus 1/24 y to the power 3 minus half y cubed. Times 2y. So now we just do a simple integration. So we get 1/3 over, we increase the power by 1, so we get 5/2. So if we divide it by 5/2, it means multiplying by 2/5 over 5/2. So we just get 7/2 reversed, 7/2 y to the power 7, sorry, 2/7 into y to the power 7/2. Here we just, if I increase it, you get 4, right? And 24 times 4 is 90 times, it's 96. And now we just increase the power by 1, so we get y to the power 4, and we divide by 4, so we get 1/8 y to the power 4. I have to substitute the limits from 0 to 4. We'll find that this is just 216 over 35, exactly the same value as if you did this thing with a type 1 integration. So this matches with type 1. Now here one thing we did is we knew from this graph that the points of intersection, the y coordinates are 0 and 4, but we might not always know that. In that case, it's very simple. We just equate the two x functions. So we just take half equals to square root y, and now we just find the y intersection point, take squares on both sides, so we get 1/4 y squared equals to y. Now we'll just do some simple multiplication and stuff. So we get y squared minus 4y equals to 0, and then y into y minus 4 is equal to 0, which means that y equal to 0 or y equals to 4, and this is the 0 point, this is the 4 point. So it's interesting that we get this exact same value. And of course the type 1 also matches with type